Hello, good morning. Oh, hello, good morning.
Yes, good morning, sir.
Yeah, good morning, everybody.
You're welcome, sir.
Yeah, thank you very much. Please, I'm sorry for the change of time. So much, I was so much constrained to change it because I initially thought our training was slated for 10 o'clock Nigeria time, but actually I was meant to start by 8 a.m. Nigerian time. It was a kind of a 1 hour time difference. So today we'll be concluding on where we uh, hello, hello.
Hello, sir. We can hear you, sir.
Can you hear me now? Okay.
Yes, we can hear you.
I thought today we are going to. Okay, thank you very much. So today we are going to finish off from where we stopped last week. Last week we looked at the topics the subtopics we looked at were one. We looked at spin. We also looked at alignment and precision. And then lastly, we looked at the principle of resonance. Just a quick recap. Spin refers to the, the state of the magnetic dipole moment of hydrogen atom or the proton. Whether we have a spin that is directed up parallel or a spin that is directed down anti-parallel, and and we um, and we're told that the hydrogen proton, or more specifically, the protons are usually around aligned in a random manner when they are not placed in a magnetic field, an external magnetic field. Just as you are, you have protons whose spins are randomly oriented in space. So you can have all manner of orientation in space. So not just spin up and down, but spins can in so many directions. So when you now place them, we come to alignment. If you now place them in an external magnetic field with a field strength, let's say V naught, the haphazard arrangement of their spins will now be much more directional. And the directions they will take will either be to be aligned up or to be aligned down. And we got to know that the spins that are aligned them up are usually more than the spins that are lying down, because the spins that are lined up actually require a lesser energy to do that, whereas the spins aligned down require a much greater energy to go down. So of course, in every system likes to take the low energy state, just like we have electrons orbiting in an atom. Electrons we normally take the lower energy state. It's only when that one is filled, the lower energy state is filled, that they go up to higher energy state. So also we have that for the nuclear materials of protons and the neutrons. So with application of an external magnetic field, the spins will now be aligned both up and down. And we did say that the difference between the number aligned up and the number aligned down depends on the magnetic external magnetic field strength. So if you have an MRI operating at 0.2, 0.3, that's 0.3 Tesla and 0.5 Tesla. For 0.5 Tesla, you have more, there will be much more difference between the number aligned up and the number aligned down, and so on and so forth for 1 Tesla and so. So when you now align them, and when they are now aligned up and down with some little difference between the number of protons up and down, they now begin to precess. They now begin to precess at a particular frequency. And as they do that, we can't use that for any MRI imaging, or even a spectroscopy. But if you want to use them for MRI spectroscopy, we have to apply an RF pulse, a radio frequency pulse, which is one of the components of the electromagnetic spectrum. We apply an RF pulse to the precessing protons, such that because when the RF pulse hasn't been applied, they all precess at out of phase. They all precess at the same angular frequency, but out of phase. But if you now apply an external RF pulse to the precessing protons, they will all begin to precess in phase. For the up one, the ones that directed up, they all begin to precess at a particular phase. And also the ones down will now begin to precess at a particular phase. That is one thing. That is the first thing that happens. And the second thing that happens is that the number of protons precessing in the parallel direction will also be the same thing as the number of protons precessing in the parallel direction. So today we want to continue from there. We now look at what happens when we now switch off the RF pulse. Because in all these things, these are just precursors to getting image on our screen. Without this special alignment and this second stage and the third stage, we are not going to have any image on our computer screen. So before we have an image, we have to remove the RF pulse so that the the protons will now begin to relax. They now begin to relax. So that brings us to the fourth subtopic we are going to look at today, relaxation. We can also call it decay. Decay. What happens if we stop applying the RF field? Immediately we stop the application of RF field. Two things will happen. The protons that were initially or rather the magnetic dipole moment that was initially fired at an angle, flipped at an angle, depending on the time of application of the RF pulse. You can have 30-degree flip, you can have a 15-degree flip depending on the energy of the RF pulse. You can have the maximum, this, which we talked about the last time. You can have the maximum transverse magnetization, MXY, when this angle is 90 degrees, which is perpendicular to the horizontal direction. We have the maximum. You could also have the something, the flip anti-parallel, that is a 180-degree application of RF pulse. But in all this, what happens when you remove the RF pulse? For 180 degrees, if you remove the RF pulse, so many things happen. You're going to have so many type of realization. Of course, basically T1 and T2. I'm going to come to that. If we are here 30 degrees, what happens when we remove the pulse? We are not going to go into all the nitty-gritty of the physics involved, but we just need to get the concept so that when we see an image, maybe when we see an image, then we begin to appreciate this concept of realization. Like I said before, you can have something can be tuned. I mean, the RF pulse can tilt the horizontal magnetization to an angle of 30 degrees, and you cut off the RF pulse, the RF signal. There's something begin to go back. You can have it at the maximum. That is the transverse maximum transverse magnetization. You cut the RF pulse, it begins to go back to the horizontal position earlier. You can also have it at 180 or even 270. There are so many things we do with the computer just to vary the contrast of the image depending on the section of the body that is being imaged. So we are going to look at the two key types of relaxation. T1 relaxation and T2 relaxation. Irrespective of where the RF pulse knocked the horizontal magnetization to, we're not concerned about that. We're just concerned about how the magnetization will go back to its maximum value from 30 degrees to the maximum horizontal from 40, from 15, and so on and so forth. So those are the things we are going to look at during this time. We have two major types of relaxation with respect to decay. We have T1 and T2. We also have one, but it is not basically it is not basically a decay mode. That is the proton density. Proton density. It is not actually a kind of a decay, but we also use it in forming the contrast of the magnetic resonance imaging. But these three, T1, T2, and proton density are actually the variables we use to get the desired contrast of the MRI image. So let me quickly talk about proton density. Proton density just has to do with the amount of protons in a particular tissue. If you have fat, you can have fat, mainly fat, water, and of course bone. These three types of these two types of tissue, they're water, because fat has water content. Bone also has an amount of water content, but fat has more than it. When we want to weight an MRI based on the proton density, fat has so much, so many hydrogen, so many protons compared to water. But bone has the least. So for a proton density weighted image, PD weighted, fat is going to appear white, while bone is going to appear, bone is going to appear very dark, whereas the water will be in between. Fat will appear white, while bone will appear very dark, whereas water will also be dark, but depending on the amount of water in that particular tissue, you're going to have a variation, a gray scaling. Excuse me. So this is just proton density. We don't have so much problem when it comes to proton density. Our major focus will be on the key realization terms or key realization components we have during the decay process. So T1 magnet, T1 realization. What do you mean by T1 realization? T1 realization is the time it takes the signal to build up to the maximum longitudinal value of B1. The longitudinal magnetization, B1. This is what I mean. You have a signal. Maybe the signal is initially zero. Initially zero. That is the longitudinal magnetization at any point. Of course, this is when you have it when it is zero, it means you have it at the transverse end. I mean the maximum transverse magnetization. The next one, you have it 90. So at this point, the horizontal component is zero. But immediately you remove the RF signal, the horizontal magnetization will now begin to build. Begins to build from zero value, say from here, zero, that's a particular point, begins to build. At this point, you have a value here, begins to build. At here, you have a value here, begins to build, and so on and so forth. At the end, you are going to have the maximum here. So this something looks, it is not a straight line, it is a curve. So you're going to take a kind of infinite time to get to the its maximum value. So the time, this time is called this time is called the T1 time, the T1 build-up. And the time required for the horizontal magnetization to reach, this is 100%. The time required for the magnetization, the horizontal magnetization to, the the vertical magnetization to reach this 67% is actually called the T1 relaxation time, or the T1 decay. T1 relaxation time. So it's going to be going gradually until it gets to 67%. Then you have a T1. You can have another T1 here, which is 67% of this. Another T1 second. You can have T1 third, and so on and so forth. But essentially, if you have up to 5 T1s, the signal would have reached about 99%. So there is no need of continuing the realization of T1 to more than 5 T1s. But when you get up to 5 T1s, the signal would have built up to around 99% of the initial horizontal, initial longitude, vertical magnetization. So in subsequent lecture, we are going to look at some of the machine-dependent phenomena of TE, and then we're going to have, I don't want to model up that here because might cause some a confusion. So today we want to look at majorly T1 and T2. So T1 is the time taken for the T1 is the time taken for the longitudinal magnetization to build up. And the time, this actual time T1 is the time required for it to build up to 67%. Fat and water have different longitudinal magnetization rates. And let me see, use this same diagram. Okay. We have to, assuming we have two distinct structures that have varying degrees of varying compositions of fat and water. We're going to have two distinct T1 core. Hello? Hello? Please, I can hear a noise in the background. You could please mute the computer. That doesn't disturb them. Thank you very much. So we have assuming we have two distinct structures inside the body that have, of course, different degrees of fat and water. We are going to have two distinct T1. For this, let's assume at this point, you have the 67% of this. 67% of the longitudinal magnetization, and for this one, you have the 67 might be here. The second one. For this, based on the T1 decay, this one is fat. Fat relaxes at a much higher rate than water. And of course, bone is somewhere down. Fat relaxes at a much faster rate than water. So if you have a structure such that you want to, if you want an imaging modality, so that you want to make it T1 weighted, you want the T1 characteristic to be highly enhanced. Fat is going to appear white. In the structure, we are going to have a fat being white, while water will be dark. It's going to give us a very beautiful contrast. And then the longer the time we allow the horizontal, the T1 to relax, the better we are going to have for contrast. But all those ones, they also have their limitations. You can't just allow the time to be so long because it's also going to affect other components we want to look at. So for fat, something is going to look white, while for water it is going to appear dark. So if you have something like the brain, a T1 weighted image of the brain, let's say you have a T1 image of the brain. The skull here, the whole of this one will be darker than the outer layer. The outer layer, which composed primarily of fat and water. So this side will be whiter than the bone. Then inside the brain, the gray matter and so on, depending on the composition of fat and water, the side is going to be dark, maybe dark matter, while the white matter with the white, signifying that, hope I'm not mixing it up. Just know that for fat, it is going, if a substance, a structure has so much fat in it, it is going to appear white when we base it on T1 weight. Whereas when it is water, it is going to appear dark. So that looked out for when the structure to be imaged is T1 weighted. Oh, look at the second. We've seen a T1 weighted. That is the time required for the um, the horizontal magnetization. I mean the vertical magnetization to reach its a peak. We're also going to look at another form of decay, which we call T2 decay. T2 decay. T2 decay is actually the time taken for the protons to begin to dephase. Because on application of the RF pulse, we have resonance. Some of the protons will now begin to align. We go to the higher energy state, which is the antiparallel direction. And as they do that, even as they do that, they begin to move in phase. So when you remove the RF pulse, another thing that happens is that even after they have reached the maximum longitudinal magnetization of the vertical, longitudinal magnetization, they are going to begin to move out of phase. Maybe initially they were all aligned along this way, all of them, so many protons.
So we are not seeing the board clearly.
Ah.
Yes. It's not on the main view.
It's not the main view.
Yes.
Is it okay now? Hello?
It's better. It's better, sir.
Okay.
It's
Sorry
okay.
about that. So we have so for 2T decay, all the protons initially moving in phase will now begin to dephase. As they begin to dephase, I can have them some this way. And as the time continues, and as that continues, at a point in time, we will now have all of them out of phase. We now have about a complete dephasing. So there's also a time that has been named to capture this type of decay. It's called the T2 decay. And it's also not a straight line. It's something that follows an exponential function, just like we have for T1 decay. So the graph takes these formats. Graph takes these formats. So this is the 2T decay. phenomenon, or the 2T decay curve. This is the time taken for the protons to completely move out of phase. And at this point, this is asymptotic to the horizontal axis. At some point, you're going to have it completely out of phase, which I give us a 0 here. So from this maximum value of 100%, a time will reach when we have the about 37%, that's about 0.37 of the protons are remaining still in phase. Around about 67 would have moved out of phase, remaining just about 37. So this time is called a T2. So this time is actually called a T2. So the time required for the phasing to be reduced to just 37%. Just remember, for T1, it is the time required for the longitudinal magnetization to build up to 67% of the maximum longitudinal value. Whereas for T2, it is the time required for the protons to lose 67% of their phase. That is, for them to just have only 37% their value left, of their pacing value left. This also is a very important realization, a very important decay we use to characterize tissues, because tissues decay. They decay T2 wisely. Let me use that word. They decay T2 wisely at different rates, just like they also decay T1 wisely at different rates. So with this, you're going to have excellent contrast. So if you have the proton density contrast, we have the T1 decay contrast. We also have the T2 decay contrast. This will give us an image that have wonderful contrast capabilities. So once also look at some the major two tissues of interest. Part what I mean three, of course, and part both, fat and water this time around. Fat decays at a different rate from water, and of course, bone. So here, this is a fat, and this is a water. Water decays at a faster rate than we look at 37% here. For 37% here, look at water. I'm going to have the T2 for water here. Sorry, water is at a longer, has a longer T2 decay. T2 for fat is around here. Of course, these values are not exact. Whereas for water, it has a much longer T2 decay. So for structures, for structural differentiation, water is going to be white. Whereas a fat is going to be dark. So this is also going to present us with a very good contrast. So, and of course, different tissue have a different water and fat rate. And before I continue, I don't know whether we have time is fast spent. I don't know what we have a few questions before I continue to the last topic we have for today, which is localization. I don't know whether any of us has any questions to ask before I continue.
Good morning, sir.
Yeah, good morning.
Thank you very much for your explanation, sir. I just want a little bit of clarification, sir, with regards to the time, the exact time of decay in terms of T1 and T2. You kept mentioning that for T1, for the time for the longitudinal magnetization to be achieved is about at 67%, and for that of the transverse magnetization, the loss of the magnitude is at 37%. I don't know if that's a slip because that does not add up to 100%. I think it should be about 37, 63%. 63 for T1 and 37 for T2.
Okay. I think that's all right. 63. But that is actually not. Well, I need to go and maybe by Friday I need to clear that. But we don't just add the. This is just a convention. It's not that you add because there are two different types of decay. It is one is T1, which is based on the return to horizontal. I mean longitudinal magnetization. That one is different from the time to dephase. The time to dephase is characterized by 2T decay, while for longitudinal, what I have to do next week is to get whether it is for longitudinal, whether it is 63 or 67. But just be clear about this that we don't just add up these two to give us any 100%. These are conventions that have been put in place for uniformity. They could have as well said the T1 is the time required for it to get to maybe 80%. And then this one, the time required for it to fall to maybe 15%. This is just a convention. But for our next lecture, I'm going to look at whether it is actually for T1, whether T1 is the time required to build up to 63% or 67%. I hope I made a little meaning.
Yes, sir. Hello, sir.
Yes.
Hello, sir.
Dr. Henry.
I was going to say the same thing. What we have in our books is 63 for T1,
Okay.
then 37 for T2.
That's not a problem. 63 for T1, that's not a problem. But all I'm saying is you don't just add up the two. I think it's just for better understanding so that if you have one, if you know one, then you know the second one. Just for comprehension, they are in no way related. You don't add up the two to get 100% because there are two types of decay modes. Any other question before we continue?
Good morning, sir.
Good morning,
sir.
Good morning.
Thank you for the lecture, sir.
You're welcome.
Hello, sir. Can you hear me, sir?
I can hear you.
Oh, okay, sir. My question is, I want to ask, sir, can you actually throw more light on what's actually responsible for the whiteness, or maybe why water is white on T1, why is the water is dark and fat is white? Are there any things responsible in the mechanism that makes them to actually differ, or what makes the time to be longer in water compared to fat in T1? I mean the longitudinal magnetization now. Are there things responsible for these things in T1, why it's longer in one tissue than the other, in T1 and in T2, sir? Then on the 63.37% that my chiefs have mentioned, though I came across somewhere that even though they are independent occurrence, but they occur simultaneously too. I mean, T1, the longitudinal magnetization, and then transversal relaxation, though they are independent, but they occur simultaneously. Maybe that's what's actually responsible for the 63.37%.
Okay.
Thank you, sir.
And you're welcome. I mean, your first question. Let's take T2 as an example, T2 decay as an example. You have water which decays a at a faster rate. Water is it is a very unique substance. For example, if you look at the ocean, if the sun heats up the ocean during the day, and then after sunset, it's going to take a very long time for the water of the ocean to return to an initial temperature. For example, it was initially at maybe 20 degrees Celsius, and it is heated to up to maybe 22 degrees Celsius during the day. It's going to take so much more longer time than the land. Let's say the land was heated to this 20 degrees, from 20 to 22 degrees. This is just an illustration. But after the sunset, this land will return to 23 degrees at a faster rate, just because of the composition of water and land. They have so many, land contains so many compounds, silicon oxide, magnesium, potassium, and so on and so forth. Whereas the ocean water is composed mainly of H2, hydrogen and oxygen atoms. So because of the different compositions of these compounds, or these compounds, you are going to have a different rate at which they cool and at which they gain energy. Also, if you want to heat water, water will take a much more longer time than that is just a part of the explanation. Then for the realization, it is because of the different ways, the different electronic, the different configurations, or how the atoms that that are in water and that are in fat are oriented. In fact, in fact, the hydrogen let's take one part molecule and so on and so forth. They're going to have this fat molecule has so many hydrogen atoms. They have so many hydrogen atoms. If you also look at water, this oxygen, hydrogen, H2O, also has hydrogen atom. The hydrogen atom here, the hydrogen atoms here, they don't receive so much shielding like the hydrogen atoms here. In fact, the hydrogen atoms here are kind of share between in the electronic configuration of this one. We have this one to be shared. So these ones are not so much protected like this. These ones are so much protected because of the electron cloud in between the carbon here and this hydrogen, carbon hydrogen. So these hydrogens are somewhat they are shielded from external influences, maybe like magnetic influence. But this one, they're not so much shielded. So because of this singular property, the time at which, if you now make this one, if you now reorientate the configuration of this one in space by application of a standard magnetic field, something is going to happen. And if you now introduce an RF pulse, another different thing is going to happen. If you now remove the pulse, a different phenomenon is going to take place. And it's going to be different for fat here, it's going to be different for water. Just because of the way they are oriented in the space, the molecules of fat and the molecules of water. Though they are the same hydrogen atoms, but just because of the way the hydrogen atoms, they combined with the carbon here, and this one, the way they combine with water here. In fact, this one is a non-polar something, whereas this one is a polar. So because of that major difference in the way the hydrogen atom is attached to the central atoms of whether carbon or oxygen, they're going to have different decay modes for both T1 relaxation, the time required for the protons to flip back to the horizontal, longitudinal magnetization, and the time required for the hydrogens here to fall back to the phase, going to be affected just because of their configuration. Now the second question he asks, T1, T2, all these processes, proton density, the number of hydrogen atoms, T1 decay, T2 decay. They all happen at the same time. In subsequent lectures, we are going to the concept of time of repetition and time of echo. They all happen at the same time, simultaneously. As this one is happening, this one is also happening at its own rate. Of course, proton density, of course, that one is a different thing. It's very, very easy to understand. As T1 is decaying, as the protons are relaxing by the method of T1, they are also relaxing with the method of T2. So in the end, when you have an image, when you have a final image, both proton density, T1 decay, and then T2 decay. That is maybe T1 weighted, whatever, T2 weighted, and proton density weighted. They're going to be superimposed on each on one another. But the trick is this: when you want to enhance proton density, all you have to do is to change the time of relaxation and the time of echo. We are going to do later. You either make this one longer and this one shorter, as the case may be. Also for T1 decay, if you want to enhance the T1 decay phenomenon, we are going to make it either tune this one to a particular value and tune this one to a particular value, so that this one will be enhanced. When this one is enhanced, doesn't mean that T2 and T proton density are not affected. They are affected, but the procedure for T1 decay will now be enhanced. Just like if you have, as you have in the case of using contrast, all those like gadolinium and so on and so forth, they are going to affect the rate at which all these things decay. So instead of having a much longer T1 decay, you're going to have a shorter decay. When you have so it all depends on the image or the type of structure you are decaying, and also depends on the type of MRI you are looking at. If it's a conventional MRI, which we do here, you see, with conventional MRI, we are looking at the anatomy. We're looking at basically anatomy. Then it's also in functional MRI. In functional MRI, want to look at how the function of one, we're looking at just the physiological functions of structures, whether a particular function is absorbing oxygen at the rate at which it should absorb it, or whether more water is moving out from a vessel at a rate which is abnormal, of course, that will give us whether the structure is diseased or not. So all these things, they are as a result of maybe choosing a weighting factor that will enhance maybe as the anatomy or the function of the the function of the image you want to acquire. I mean, the function of the structure. I don't know whether that answers it to an extent.
Yes, sir. Thank you very much. I really understand the explanation, sir. But one more thing, sir. Does it have to do with exchange of energy between the precessing protons or relaxing protons and the surrounding environment?
Of course, of
Is there
course,
any?
of course, of course. Like
Okay.
T1 is spin. Um, yeah, T1. I'm sure about that. Okay, T1 is a spin. Okay, spin lattice.
Spin lattice.
T1 is a spin lattice. So it depends on how energy is given back to the surrounding tissue. How energy is given or back, given off to the surrounding tissue, because when you introduce the RF pulse, energy is going to be deposited inside the tissue. When you now remove it, the energy will be given off to the lattice, and of course, it can cause some heating effect. Whereas for T2, it is basically spin. For T2, it's actually spin and relaxation. So that one is basically is it has to do with the inherent magnetic property of the atom of the protons and themselves. We also have a, a T2 the T2 star, which I'm going to look at now. Well, before I move to that, you have uh, have I explained is have I explained it to at least to an
Yes, sir.
extent? Okay. Thank you very much. Where do we stop off? So the T2 and the T2 we looked at, we described earlier, is a perfect T2 decay. In actual fact, what we normally have is T2. What we normally have is the T2 star. T2 star is actually the normal T2 decay, which accounts for the inhomogeneity in the magnetic field of the tissue, because the field, the external field introduces also has its own magnetization, which is not uniform, and because of that, it's going to have an effect on this T2 decay. So the enhanced T2 decay, which is impure, is the T2 hash, which is as a result of inhomogeneous magnetization of the surrounding tissue. Let me just stop at that. Oh, I have, wow. Wow. Time has been passed. I need to prepare for I think at this point it's almost 8:26, and I think we should call it a day. Maybe on Friday we look at localization. How do we determine the slides we want to image. How do we determine that? Is it with the processes we have outlined them? We have explained them earlier. Or how do we actually localize um, a section to be imaged in an MRI? How to be focused maybe on physically on the Friday. But before then, what we call it a day, I would like I will entertain questions. If you have some questions we want to ask based on a previous lecture, and then this one we will do that for purposes of a better comprehension. Any question? Hello?
Hello,
Can you hear
sir.
me?
No questions.
Hello?
Yes, sir.
Hello?
Hello, sir.
Hello, can you hear me now? I'm sorry, I mistakenly
Yes, sir.
turned down the volume. I said, do we have questions to ask before we wrap it up? Because in our next concluding lecture on this topic, on this subtopic, we are going to be looking at the localization. So before then, do we have questions on what we have done so far, and even from our last lectures? Okay, I want to believe that we don't have any other questions. So we are going to be looking at localization in the next lecture, and we also look at the physical components of an MRI. Physical component of MRI. I want to wish you a wonderful day ahead. Thank you very much.
Thank you, sir.
You're welcome. All right. I'm sorry. I think you have some charts here. I'm sorry. It's not easy. Going through all your charts. From our next lesson, we are going to have a co-host. So we have one of our some other medical pieces that will be co-hosting. So if you have some questions, it could also help us even from their end. So and there's some of the technical aspects and so on will also be will also help us out. Our co-host will also help us out on that. And if you have some sections that need further clarification from the end of the co-host, we are also going to have that in our next lesson. So till then, I want to wish you once again a blessed day. Bye-bye.